Hi, my name is Frederic Green, and I'd like to talk about my paper with Amitabha Roy, Uniqueness of Optimal Mod 3 Polynomials for Parity, that is to appear in Journal of Number Theory. Our original motivation is to prove lower bounds on certain types of Boolean circuits. And for the Boolean circuits we're interested in, that reduces to proving upper bounds on a certain class of exponential sums, which is the focus of our paper. These sums have the following form. We sum over n variables, each of which can be 1 and minus 1, and what we sum is the product of those variables times a complex mth root of unity, omega raised to the power a polynomial p of x1 through x sub n. And we have an overall normalizing factor of 1 over 2 to the n. Let's call this sum s sub m of p and n. Now, it's immediate in the case that m is equal to 3 that this can be written as a multiple Gauss sum. If you take chi as the quadratic character, then the x's can range over all of C3. And in fact, for other moduli with some work, you can show that multiple Gauss sums are also relevant. So this is a type of object that is intensely studied in number theory. The kinds of asymptotics that we're interested in is that the degree of the polynomial remains small as n goes to infinity. In particular, we believe that if the degree of the polynomial is as much as log n to a constant, that this whole quantity will be exponentially small. Some evidence we have for that comes from the fact that we know it's true when the polynomial is symmetric. When the polynomial is general, we know considerably less. Here's what we do know. In a paper I published in 2004, I showed that in the case m equals 3, that the norm of this quantity is most the square root of 3 over 2 to the n over 2. And this is in the case when the polynomial is quadratic. Now, also, this bound is tight. You can't do any better than this. But curiously, the technique I used for this only worked for m equals 3. And one would expect that it would be true for other m. And indeed, something like it is. In a really dramatic result by Bourgain in 2005, he showed that you get exponentially small upper bounds for any odd m. In fact, the degree of the polynomial can even be non-constant. In fact, it could also be some constant times log n, where that constant is less than 1. However, we still don't know about our original belief that this polynomial can have degree log n to a power. And it doesn't seem that this technique will get us to higher degrees. So for this reason, we revisit the quadratic case in the interest of getting sharper techniques. And around the same time, in a paper by Duenas, Miller, Roy, and Straubing that appeared in Journal of Number Theory, they looked at the quadratic case and indeed obtained exactly the tight bounds you would expect for quadratic polynomials in all odd m, but only going as far as 10 variables. In proving this result, they found that there were some properties of the sum that were particularly useful. First of all, the polynomials that give you the largest value for this quantity, what we call optimal polynomials, are unique up to relabelings and constant and additive constants. And also, any suboptimal sum is at most some constant less than 1 times the optimal sum. In the case of m equals 3, that constant is in fact the square root of 3 over 2. Our result is that we prove their conjecture for m equals 3 and all n, not just up to n equals 10. So we have a complete characterization of the polynomials that make this sum maximum. The shape of the polynomials is like that, and that is the main result of our paper.